Okay, good day everyone. No matter where you are, and welcome to this webinar. And this is the fifth event. The topic will be related to quantum computing and the design automation challenges and opportunities. So this webinar is organized by Professor Yilan Chen from Duke University and me from National Tsinghua University, and I work for CEDA and Yilan work for SIGDA, and we also got a sponsorship from Synopsys. So for today's program, originally we plan to have 4 speakers, and we are fortunately enough to have Professor Anupam Chattopadhyay from Nanyang Technical University. And originally we have 4 speakers, but unfortunately today, I just received an email from the Professor Camila today, and her daughter's classmate is commit the case of COVID-19 yesterday. So she needs to take her daughter to hospital to do the PCR test today. So unfortunately, she cannot join the webinar today. So today we have 3 speakers. The first speakers, we are fortunately enough to have Oliver Dial from IBM. So he will talk about the general introduction about the quantum computing. And also we have a speaker from Cambridge Quantum, Dr. Ross Duncan. Yeah, he will talk about the quantum compiler. And last but not least is Professor Robert Wheeler from JKU. As all you probably know that he received the Best Paper Award of TCAT this year, and the topic is related quantum computing, EDF for quantum computing. So he will talk about this topic, and hope everyone will enjoy the webinar today. So first, I will give a brief welcome remark, and then I will hand over the floor to Anupam, and then we will have the first talk. As I mentioned, we will have Oliver to talk about the general introduction on quantum computing. Then the next speaker will be Ross, talk about the NISQ computer, and the last one will be the Robert, talk about the design automation for quantum computing. Okay. So currently we have the CEDA and the SIGDA. We actually have the 2 call for nominations. So one is for the CEDA Ernest Koo Early Career Award. The deadline will be the April 15. So if you and your colleague will be interested in this award, please try to submit your nomination case. And also we also have next year we also have the Asian IEEE Richard Newton Technical Impact Award on EDA, and the deadline will be February 1st. So last is that we actually need we hope we can have more members who will be the volunteer and also join the community of the SIGDA and also the CEDA, and all the CEDA video. We will consult the speaker today. After receiving their confirmation, we will put the video on the CEDA and SIGDA video repository. Okay. So now I will hand over the microphone, the host, to the Anupam to moderate the event today. Okay, thank you, Anupam.
Yeah. Hello everyone. Welcome to the webinar today, and thanks to Shunhee and Iran for organizing this. It's a very, very timely topic with lots of exciting research happening around, and thanks to the speakers that they agreed to present their latest research on this. So without much deliberation, I now move to the first talk for today. We have Oliver Dial, who is a technical lead for quantum hardware in IBM Quantum, with research focus on novel and high-performance multi-qubit systems. At IBM, he's worked on qubit coherence and gates in both 2D and 3D Transmon systems. He joined IBM in 2012, having first entered the field of quantum computing as a postdoc at Harvard by demonstrating the first 2-qubit gate between semiconductor singlet, triplet qubits, and also providing the benchmark charge noise data for these systems. So Dr. Dayal received his PhD from MIT in 2007 for research in two-dimensional electron and hole systems. So I welcome Dr. Dayal to now share his screen and go on with the presentation. And for the audience, you can put your questions in the chat folder. In the Zoom, there is a chat option, so you can put your questions there. And after the talk is over, we will have 5 minutes question and answer session for each speakers. But since we have less number of speakers, so we can make some little leeway with that and can ask more questions if discussion continues. And at the end, we have a particular time slot for general questions to all of the speakers. So you can also reserve some questions for that time. Okay, so Oliver, you can go ahead, please.
Oh, it's a dangerous, dangerous thing to tell speakers that there's some excess time that they might make use of. I hope you don't regret that choice. So anyway, good morning, everyone. I'm going to talk to you today about quantum computing and design complexity. I'm going to start out with a general introduction to quantum computing that's going to kind of go at warp speed, and then talk a little bit about some of the hardware systems that people are exploring to implement quantum computers. Then we're going to very quickly dive down a little bit deep into the type of hardware that we're making at IBM and a lot of research groups are making, just to look at some of what I see as the design challenges that we're going to face as we try to scale these systems up. But before we do that, I would like to thank the organizers. It's really hard to foster a sense of community these days. And we really appreciate the fact that you're making these efforts to try to help us all out. So what is quantum computing? Why am I excited about it? Why do I think you should be excited about it? Why is my slide not advancing? These are all great questions. So it's tempting to think of this as sort of an extension of Moore's law, that we're all worried about the end of scaling, that we're hitting the limits of CMOS, that it's going to get harder and harder to make faster computers. And so you might think, well, quantum computing is clearly where we're going to go when CMOS stops scaling, but it's really probably not. And to explain this, I'd kind of like to talk for a moment about the Church-Turing thesis, the idea that any classical computer can emulate any other classical computer in polynomial time. And what that really says is that if I want to introduce a new computational technology, I'm not really competing on what that computer can do, because really a computer made out of mechanical relays or vacuum tubes or integrated circuits or even carbon nanotubes, if you're a little bit zany, can do anything that any of those other computers can do. They're really competing on speed, they're competing on cost, they're competing on size, power, reliability. And that's a really hard field to enter, because anytime you want to propose a new technology there, you're struggling against this behemoth of extremely advanced processing technology and advanced packaging, and just this enormous depth of knowledge in how to build silicon computers. What I think makes quantum computers a little bit special is that we try to break that Church-Turing thesis. And here I'm going to use an argument that's adapted out of Scott Aronson's PhD thesis, and it's based around the existence of something called Shor's algorithm, which is an algorithm for quantum computers that lets you quickly, in polynomial time, factor large numbers. Now, there is no known classical algorithm for factoring large numbers efficiently, and so that tells us one of three things has to be true. One possibility is quantum mechanics might be wrong. It may be that we're never going to be able to build a quantum computer because there's something fundamental about the universe we don't understand. That would be really exciting. That would be a Nobel Prize for somebody. Awesome. Another possibility is that actually factoring is easy and we've just never found the efficient classical algorithm for it. That would be another really amazing result. Someone would get to go someplace very special if that turns out to be true. Or the final possibility, and the possibility that most of us that are trying to build these computers believe is true, is that the strong Church-Turing thesis is false. Actually, it is possible to build a computational device that cannot be efficiently simulated by a classical computer. And we think that this device is a quantum computer. Now, that doesn't mean that a quantum computer is going to do all of the jobs that our classical computers do today. In fact, the quantum computers people are proposing today are in many ways horrible. They have very low clock rates. They don't have very much storage. There's really doesn't seem to be a lot of potential for them ever to be competitive with classical computers on those bases. And so what they really, you should think of them as, is a special purpose processor that's really good at some specific problems and domains that classical computers aren't good at. And so this is really something that's going to sit along the side of a large classical computer to help you solve particular problems that they're good at, not a replacement for your classical computer. So how do we make this beast? Well, the first building block that you need is something called a quantum bit or a qubit. And what this is a physical two-level system that can take on one of two states, but we're going to label 0 and 1. In a lot of cases, it's the ground and first excited state of some system like an atom or an oscillator. But the really cool thing about a qubit that makes it different from a classical qubit is that we're going to isolate it so completely from the rest of the universe that we can actually prepare it in a quantum superposition of 0 and 1 and have it stay there. And so what that means is the full state of a qubit, instead of just being it's in the 0 state or in the 1 state, is that it's some probability amplitude alpha times the 0 state plus some probability amplitude beta called the 1 state. And I'm using the words probability amplitude very carefully there because in addition to just a probability, there's a phase associated with this. And so we can describe the state of a qubit as a position on the surfaces of a sphere, where conventionally people will put the ground state at the north pole of the sphere, the 1 state at the south pole of the sphere. And for example, these superpositions where alpha and beta are the same 1 over root 2, so the same probability of being in the 0 and the 1 state, but they have different phases like 0 plus 1 or 0 minus 1 or even 0 plus I1, are these states around the equator of the block sphere. And to make a qubit, we need to be able to do quantum operations that can move us around this space. So for example, for a classical bit, we like the NOT operation that maps 0 to 1 and 1 to 0. For a qubit, an equivalent might be an x pi pulse, which rotates the state on the block sphere by 180 degrees around the x-axis. And so it looks a lot like that classical NOT gate if you're working on 0 or 1. But for example, if you had 0 plus 1, it would map you to 0 minus 1. The second ingredient that we need is a way to take multiple of these qubits and put them together and have operations between them. And much like in classical computer, you can, instead of talking about all possible gates, you can talk about a universal set of gates. But we can do the same thing for these quantum computers. And one particular 2-qubit gate I like that's universal is the C0 gate, which says if qubit A is in the ground state, don't flip qubit B. If qubit A is in the first excited state, do flip qubit B. And so, for example, with the C0 gate, I can go from that equal superposition we were talking about before and make a Bell state, where I have 2 qubits which are either both in the ground state or both in the first excited state. But there's no possibility of finding them in opposite states. So really, the power of the quantum computer is not going to come, it comes from when you put all these things together, what you end up with is a state space that's exponential in the number of qubits inside of it. And the quantum computer can be in any or all of those states at the same time. If we were reading a popular news article, at this point, it would probably say something like, well, and then we prepare a superposition of all possible inputs, and we run a classical algorithm, and we get all possible outputs. And so we find out all the answers at the same time. And well, you could sort of do that. You can run classical reversible logic on quantum computers, and you would get out all possible answers. But there's no way of telling, they're all mixed together. It doesn't do you any good. And so if you want to design a quantum algorithm for one of these computers, you need to make something very special. What you need to do is start out with an n-qubit state, and then you can run these quantum operations. And here on the picture on the right, that's all these little boxes with U's in them, and some of them affect 1 qubit, some of them affect multiple qubits. And you can think of all of these paths of information through this quantum algorithm as interfering paths through this probability amplitude space. You need to design it so that the right answer gets positive interference, constructive interference, and occurs with high probability, and all of the wrong answers that you're not interested in get destructive interference and occur with low probability. And so our quantum algorithm then is something that starts out with an n-qubit state. It goes through this exponentially large space, and then it constructively interferes out the n-qubit answer that you're interested in. It takes a very, very special sort of mind to be able to describe these, design these algorithms. There aren't actually a whole lot that are known, but the ones that are known about are actually can be quite powerful. So what kinds of things can we do? Well, first of all, for details, there's this website at the bottom, Quantum Algorithm Zoo, which is kind of fun. It's a listing of all known quantum algorithms. But very schematically, we can divide the world into two kind of areas that are interesting. I mean, of course, there's an area of easy problems, like what's 1 + 1? We don't care about those very much. There's problems that are hard for classical computers, and then there are problems that are hard for possible for quantum computers. And the really interesting thing is that there are problems that are hard for classical computers that are easy for these quantum computers, what's labeled quantum possible on this. Some of these occur in areas like number theory, like factoring I mentioned before. Some of them fundamentally have to do with simulating quantum mechanics using quantum systems, like applications in chemistry and material science and quantum mechanics. There are also problems in machine learning and optimization. And so if your problem is in one of these areas, there is a good chance that there's a quantum algorithm that's going to help you. And if we wanted to get a little bit more rigorous about this, there's a class of problems called BQP, which are problems that a quantum computer can solve in polynomial time with bounded probability. They don't always give the right answer. And three of these problems that are kind of interesting is the ability to solve large linear systems, quantum material systems, and quantum locks. And the reason why I've called those three out is those are what are called BQP complete. So that means they're as hard as the hardest problem in BQP. You can map any problem in BQP into these. And so these are the problems that we suspect or know are exponentially faster to solve on a quantum computer than on a classical computer. There are also some problems that are in BQP, but probably not BQP complete. This includes that factoring problem I mentioned before, also semi-definite programming, which shows up in a lot of optimization problems. These are not BQP complete, but they do show an exponential speed up compared to the best known classical algorithms. So this is another area you should be thinking about if you're thinking about a quantum computer. So running a quantum algorithm in practice then looks a little bit like this. We start out with the problem that we want to solve. We write a classical algorithm which converts that problem into a quantum circuit that runs on some big classical computer that's attached on the side of your quantum computer. Then you run your quantum circuit on your quantum computer, which is a special piece of hardware sitting off to the side or someplace in the cloud. And possibly there's also some what we call near-time compute associated with this, where you measure qubits in the middle of a circuit and act on them, kind of some feedback built in. And then finally, you get some classical data out, which gives you your problem solution. So this probably goes without saying, if you're going to do this efficiently, you need some quantum hardware. The entire reason why this is interesting is it takes exponential classical resources to simulate arbitrary quantum circuits. So what are the types of quantum hardware people are playing with? Well, what's your favorite qubit? One general class of qubit that people are playing with, and the requirements here is that you have a physical system that you can both control and control quickly so you can run your quantum algorithm, but still isolate it from the rest of the universe so you can maintain the superpositions. One class are based on atoms. These would be the trapped ions, solid state defects, neutral atoms. Here, your quantum state, your qubit is going to be either two different excitation levels of these atoms, or even in the case of trapped ions, mechanical motion of the atoms inside of the trap. We manipulate them using lasers. We manipulate them using electrostatic gates. In the case of ions, we can actually shuttle them around. And so running a quantum circuit will look like getting a set of atoms or trapping a set of atoms, and then shining a series of laser pulses or hitting them with these electrostatic gates to move them around. Second class are based off of photons. We talked about interference at the beginning as a model of quantum computing, and so it's a little bit unsurprising you can actually make an interferometer that does this, where qubits are now photons, either their existence or absence, or the polarization state of the photons. And we create our algorithm by creating a series of careful beam splitters and mirrors and polarization rotators on an optical table. The third implementation is based on electrons, either in quantum dots or nanowires. And here we store quantum information typically in the spin of the electrons. You could in principle do it with the charge, but that's very hard to isolate from the rest of the universe. So these electrons have a little tiny magnetic moment, and we can manipulate those using electrostatic gates near the electrons, kind of like a field effect transistor, or using microwave pulses that interact with that magnetic moment. Finally, you can build the type of qubit that I'm most familiar with these days, which are based around superconducting circuits. And here, our qubit state is actually stored in the absence or presence of a microwave photon inside of an oscillator. And we make those oscillators a little bit nonlinear so that we can isolate that 0 or 1 photon state for the rest of the excitation manifold. Now, something funny you might notice about almost all of these systems is that they look a little bit different from classical electronics, where you have some state that flows through a circuit from, across the chip. That here our qubits are sort of stationary objects, and we implement our gates by driving operations on them using external lasers, microwave pulses, electrical pulses, that kind of thing. And so it really separates out the problem of how do you make a quantum computer to solve a particular problem into two separate parts. First of all, there's the part of what is the underlying hardware, the physical system that I'm going to use to make my qubits. And the second is, how do I do the control of those qubits to implement the quantum circuit that I'm interested in? I think there are going to be a couple of talks later on the details of how you optimize these quantum circuits. But it is important to realize that ultimately this circuit turns into this set of microwave pulses, light pulses, anything that's going to operate on these physical devices. And that's why we call these universal gate-based quantum computers, because by choosing different sequences of these pulses, you can get it to do any quantum circuit that you would like to do. Now, the hardware itself actually has limitations. For example, here's a map of one of our quantum devices, and those little arrows are saying that we can only run 2 qubit gates between those pairs of qubits. And so if I have a specific generic quantum circuit that I would like to run, I need to do some adaptation of it to get it to run on the actual hardware. And I need to do 2 different types of adaptation. First of all, my generic circuit might have any quantum gate imaginable. My hardware can probably only do a subset of those, hopefully a universal subset. And so I need to map the gates to gates my hardware can actually do. Secondly, I need to map the topology of that circuit into the topology of my actual hardware. And again, I think we're going to have some talks on the details of this later on. I'm just going to say very briefly, this is a critical step, that having a good, in IBM's preferred language, transpiler, can make the difference between a quantum computer, which almost always gives you the correct answer, and a quantum computer, which gives you an answer that's indistinguishable from noise. Now, if you're used to classical electronics, that might seem like a strange statement, because it shouldn't matter whether my solution is efficient or not, and whether or not it gives me the right answer. But it turns out that every quantum computer that we make today isn't actually that good, that we talk about a gate fidelity, the probability that any one of these quantum operations that gives the right answers, and those are floating around 99 or 99.9% fidelities these days. And so if you run too long of an algorithm, you will get the wrong answer. And this ties back to the fact, if you imagine those microwave pulses, these are analog pulses. If you imagine that block sphere of all the different states that a qubit could take on, this is a fundamentally analog computational paradigm. And so we just can't implement it in the physical world with arbitrary precision. What we need to do, if we want to run the really complicated algorithms that are going to give us answers to problems that we care about, in the most general case, to be able to run any of those algorithms, all of those algorithms I was mentioning before, is to begin to build error-corrected quantum computers. These are a really cool set of techniques for taking these analog errors and projecting them out into digital errors that we can correct. So we can turn these analog, I rotated a little bit too far, not quite far enough type of mistakes into the qubit is flipped, for example. But there's 2 caveats here. The first is that none of these have been demonstrated experimentally in their full scope, in the scope of actually being able to run one of these circuits with them. And secondly, they all have what's called a threshold. There's a fidelity that you need to reach before they do more good than harm. And we're floating right near those thresholds these days. And so we're not quite ready to try these error-corrected algorithms. And the final caveat is they require a lot of qubits. Overheads typically range from 16 to hundreds of physical qubits per error-corrected logical qubit. And so we need to be able to build quantum systems much larger than what we build today. So what does a quantum system we build today look like? Well, here's one that we build at IBM. This is a superconducting qubit called a Transmon. And what you see here in this picture is 2 niobium metal paddles on top of a silicon chip that form a capacitor. In between those, too small to see here, is a Josephson junction, which is just a superconductor insulator superconductor tunnel junction. It turns out in the correct limits that Josephson junction looks like a nonlinear inductor. And so this entire thing makes a nonlinear LC circuit. We designed this circuit to have a resonant frequency of around 5 gigahertz because we can get cheap, good microwave control at that frequency. And the fact that the Josephson junction is nonlinear means that the energy spacing between the 0 and 1 photon state is a little bit different from the energy spacing between the 1 and the 2 photon state, about 300 megahertz actually. And so what that means is I can make a precisely calibrated microwave pulse with exactly the amount of energy it takes to drive this qubit from 0 photon to 1 photon and apply it. If I apply it a second time, it's not able to go to the 2 photon state because it's off resonance. And so actually what I get is stimulated emission that drives me from 1 photon back down to 0 photon. And this is how on a superconducting transmon qubit, I run that xpi rotation that I mentioned at the beginning of the talk. I can couple together a bunch of these using capacitive or inductive or resonant networks. And then I can use a similar set of techniques to get 2 qubit gates and to get universal operation out of a device like this. And so here's sort of a picture of a relatively simple 16 qubit device made in this technology. You can see the qubits here. You see resonators providing that network that connects them all together so I can run my 2 qubit gates. You can see some additional resonators over here that connect the qubit to the outside world. And those play 2 roles. They protect the qubit from the outside world, but they also allow me to measure the state of the qubit because it turns out the frequency of that resonator will depend very, very slightly on the state of the qubit. So when I want to know the answer at the end, I can get the answer. Now, devices this size we can lay out by hand relatively easily. Once we've laid them out, we need to make sure that we're able to run our quantum algorithm. And so we need to be able to go from a picture of a chip like that into a qubit connectivity graph, as well as a set of instructions as to what the Hamiltonian looks like, the quantum description of the devices, so we know how to control it. And then finally, once we have that, we can adapt the quantum algorithm to this particular chip. So to do that, we need a bridge between the classical description of the chip, something that we can use our current EDA tools to construct, and the quantum description of the chip in terms of what the energies of the qubits are, what the coupling matrices of the qubits are, what the coupling matrix is of the qubit to the environment. We do have tools to do this today. There's a lot of different approaches. The simplest is if I can draw an equivalent circuit in terms of inductances and capacitances, I can directly write the Hamiltonian out of that because we know what the quantum mechanical behavior of inductors and capacitors is well enough. And so there's systematic techniques for doing that, such as the method of nodes that's outlined in that Devray article. There are even EDA tools that are open source where I can draw a circuit like this and it just writes down the Hamiltonian for me. Our real devices typically have too many contributions from distributed elements for us to be able to easily write down that equivalent LC circuit though. And so that brings us into using full wave electromagnetic solvers to try to figure out what our devices are going to do. If you have an eigenmode solver available, like on the far right, it turns out there's a very simple mapping of those eigenmodes back into the Hamiltonian because really you're just talking about energies when you're talking about the Hamiltonian. On the other hand, a lot of the time, the easiest thing to get is the response function, the impedance of the device as a function of frequency is seen from the qubits and is seen from the environment. And it turns out from that, there are techniques that you can use to extract either an equivalent circuit that we know how to quantize, or what's really powerful is there are even approximate impedance functions where I can go from the value of the impedance, that some frequency, directly to the kind of quantum parameters I care about. And the reason why that last one is so powerful is that means I can use conventional microwave design tools and optimize for the quantum properties that I want to see. Anytime I have to step outside of that into these equivalent circuit techniques, it means that I have to put a human in the loop. I have to move back and forth between 2 tools and I really break up my design flow. So why am I a little bit scared of designing these? Well, if we want to build logical qubits, we're not building devices with 20 or 100 or 1,000 qubits. We're designing devices with millions of qubits. And what that means is that simple 2-layer approach that I saw you before breaks down just because there are too many signals involved. In most of these technologies, you have basically 1 I/O line per qubit. And so if you look at the types of devices people are planning for the next 2 years, you're beginning to see these complicated flip chip designs, integrated multi-level wiring, integrated 3DI, 3.5DI, 2DI. And this isn't some hypothetical. At the bottom left, I have a picture of IBM's current quantum processors with some 3DI involved. At the far bottom left, I have a superconducting multi-level wiring we're building in the lab today. And the complexity of these designs rapidly goes past the point where we can accurately make them by hand. We really need better tools to be able to get these devices to continue to work. Moreover, as we add all this complexity, the build cycle for these devices gets quite long. And so the penalty for making a mistake is becoming extreme. And so we really need to start working on better tools today. So this is a really exciting time to be in this field, that a lot of these ideas that used to be theoretical are now showing up in the lab. And if you don't have a lab full of quantum computers, you can even now go on the internet and use a lot of these things remotely. So if you're interested in quantum computation, I strongly encourage you to take advantage of the fact that many, many people now let you play with a quantum computer by yourself. It's wonderfully fun. It's a good thing to do if you're stuck in your house. And I hope you're as excited about it as I am. Thank you.
Thanks for the overview presentation. It was quite interesting to know about the latest activities from IBM. So the floor is now open for questions from the audience. If someone wants to ask something, you can temporarily unmute yourself and ask the question. Maybe type in the chat box for all to see. Okay, I think, Oliver, one general question that probably everyone's is willing to know right now is, how do you see the scale up of the quantum computer? Is there something like Moore's law that you are pursuing? And how do you decide to select between different kinds of qubits?
So there's two need to improve the fidelity. 99 to 99.9% number I quoted you, it's close, but it's not there. Most people think for practical error correction, we want to be right around 4 nines. And that's really the driving force that we have between different types of qubits, at least between different types of superconducting qubits, is what we think can reach that number. And we're limited by many things like the losses in the materials involved in the devices, the engineering of them. The second type of scaling that we need is to increase the number of qubits so that once we do have these error correcting algorithms working, that we can actually solve a useful computation. And those really require different types of research. That first one is more fundamental basic research. The latter one is taking the packaging technologies that's already been developed for the semiconductor industry and using them to scale out the device. So we're trying to pursue both of these at the same time and hoping that we can kind of merge these two technologies together once we're ready to roll. In the meantime, we are trying to use a metric called quantum volume as sort of a standard way of talking about how powerful a processor is. And you can think of that as, let's imagine I had 1 qubit that was perfect. It's useless because it's only 1 qubit. I can't do a computation with it. On the other hand, if I have 1 million qubits that are horrible, they're also useless because by the time I make a state that spans all 1 million qubits, I've made too many errors to ever recover. And so quantum volume tries to capture what's the biggest useful Hilbert space that you can explore. Sorry, what's the biggest useful number of qubits that you can use in running an algorithm, whether it's limited by the number of physical qubits on the chip or limited by the fidelity of the gates. And it tries to make you prove that by actually running a trial algorithm with that number of qubits and demonstrating that you got the right answer. And so we are trying to maintain a Moore's law-like speed up on that quantum volume. According to our roadmap, we're supposed to double it every year. We quadrupled it this year. So we hope our management doesn't expect us to continue that rate of progress, but we're quite happy about it.
So you already see some kind of scalability similar to Moore's law, like doubling or something like that, number of qubits or quantum volume, as you said.
So doubling the quantum volume, it's a little bit of a hedge. It means adding 1 effective qubit a year.
I see. So okay.
It's a roadmap we can stick to, but at some point we need to greatly exceed it.
Okay. And since it's the community here that gathered is mostly from EDA and SIG, so one relevant thing that you also showed in your slides is the necessity of transpiler research. And I know IBM Qiskit is giving us a great forum to start with. So you can say something about this, like how relatively inexperienced or novice person who knows about EDA but wants to jump into quantum EDA can take the advantage of IBM Qiskit and directly start programming into the cloud IBM quantum computers.
Wow, you're practically doing my job for me. This is great. Yeah, so it's a lot of infrastructure needed to run a quantum computer, going from the way of describing the abstract algorithm, transpilation to the hardware, the control of the hardware itself. And so with Qiskit, what we try to do is make an open source stack for doing this entire job. And there's 2 things that are really great about that. One is that it makes it really easy for people to get started. There are tutorials, there's some information here. And so you can pick just the part of it that you're interested in and dig into it and have somebody else already provided the entire rest of the stack around you so that you don't have to do this whole thing yourself. If you're interested in the transpiler, you can add, it's a pass-based transpiler. You can add a pass yourself, and then you can use tools other people have written already to look at the effectiveness of it or even test it on real hardware.
Okay.
The second really great thing is there's a big problem in research always with stickiness, that somebody accomplishes something amazing for themselves, but it's very hard to get it out into the community as a whole because there's no common platform to build off of. And so you sort of make an advance and you step back, and you make an advance and you step back. And by providing this open source framework that people can add passes to, add their own research to, what we're hoping to do is to help create this stickiness so that when somebody does research in this framework, they're helping everyone else that's working at every layer of the problem.
Okay. Okay. That's great effort, actually. Yeah. So any further questions from the audience?
I want to ask a question. So,
Sure.
In quantum computing, do process variations of the device affect the computing accuracy similar to the process variation in IC design? Is it similar, or we don't have the process variation problems in quantum computing?
There are definitely process variation problems. The way that they enter depends, I don't know how that happened. The way that they enter depends a little bit on the exact type of processor that you're building. For example, in spin qubits, one of the big problems is you're trying to trap a single electron between some electrostatic gates. And so if you have a charge defect in the vicinity, it will tend to grab that electron before your gates do. In the type of qubits I build these days, transmons, at IBM, I didn't go into detail about what sets the frequency of those transmons, but a key parameter is the critical current through that Josephson junction, basically the resistance of the junction. And because we build fixed frequency transmons to get our devices to work, we need to control that junction resistance to make sure that adjacent qubits don't come out at exactly the same frequency. It turns out that to do that, we need about 0.5% control over that junction resistance, which is in microfabrication extremely difficult to attain. In fact, we don't have it yet. We're sitting at about 2%. And so that process variation on that junction CD and on that junction thickness, the resistance of it, is one of the key contributors to errors in our processors today.
Okay, thank you.
So we got one question also from the chat window from Al Tamimi. Are there any tools or quantum programming language or compiler that one can use to create a quantum block? So I think it's already discussed when we were talking about keyskit, but maybe you can just reiterate that.
Yeah, so keyskit is one language. In fact, for getting started, there's even a visual composer where you can draw a picture of those quantum circuits like I was showing and just play around. There are a lot of quantum programming languages out there, all with their different pluses and minuses, and I wouldn't presume to make that choice for you. But keyskit.org is certainly a place to get started.
Okay, so if there are no further questions, then I would like to thank Oliver again for taking these questions and participating in this session. So,
may I ask a naive question?
Yes.
Okay, thank you. Yeah. Okay, this is Haizo from Northwestern University. Yeah, I think on one page of the slides, you talk about I think the 3 possible states of the kind of quantum mechanics run. My naive question is actually from the news. We heard the quantum supremacy from Google, and I think recent news also from China. So does that mean that possibility is already run? Means it already showed that actually quantum computing actually is super than classical computing?
Yes and no. I mean, I would take both of those as extremely strong evidence that quantum mechanics is right and that this Church-Turing hypothesis doesn't apply to quantum computers. It's worth recognizing that both of those demonstrations were a little bit what's the best word to use here? Academic, in the sense that instead of picking a useful problem that somebody would like to solve and solving it, they created a problem that's hard for classical computers, picked a problem out of that they were able to run on their quantum computer, not even necessarily one that was selected in advance, ran it, and then were unable to simulate it classically or unable to easily simulate it classically. And so they're wonderful demos. The technology that goes into those is really amazing, but there's still a big step to go from those to quantum computers that can solve a useful problem that you choose in advance that you care about. Does that make sense?
Great, thanks. Great.
Okay. Okay, then Oliver, thanks again for being with us, and please stay because we will be having a panel towards the end of the session. Okay, so thank you, and thanks audience for this engaging discussions. I will move to our next speaker now. This is Dr. Ross Duncan. Ross Duncan is the head of quantum software at Cambridge Quantum Computing Limited and permanent research fellow at the University of Strathclyde. He obtained his doctorate from Oxford in 2006 for his thesis on types of quantum computation. Since then, he has held positions as EPSRC postdoctoral research fellow at the University of Oxford, charge de recherche at the Université Libre de Brussels, and the lecturer of computer science at the University of Strathclyde. His research focuses on the foundations of quantum computing, in particular the use of category theory and diagrammatic calculi to better understand.
To segue into Connell's discussion that he wanted to have today.
Yeah.
Sure. Yeah, yeah. I can take it. Are there any questions? I guess up to this point. Right. Anything else I should go over? Did Oliver just join? Yes.
Yeah, I did. I'm sorry, the conference started late, so I ran a little bit late.
Does someone want to tell Oliver?
I can have a separate meeting with you, go over what we talked about, if you have time.
That would be absolutely
fun. Okay.
Okay. Yeah, so among other things, I think the most interesting contribution from Ross is the invention of JEDEX calculus that he has applied to reason about quantum circuits and measurements. And his current research focus is on the development of pytket, that's on the platform, which is independently optimizing the compilers and software development framework for near-term quantum computers. So thanks, Ross, for being with us today. So we're looking forward to the presentation.
Great. Thank you for the introduction. It's very kind. I will now try to share my screen. So let's see if this is going to work. And that should be that one. Okay, and now if I...
Yes, we can see that. Yeah.
And do you see the presenter view now?
Yes, yes, perfect.
Okay, great. So thank you very much for the introduction, Anupam, and thank you to the organizers for inviting me to take part in this event. So my name is Ross Duncan, and I work for a small company called Cambridge Quantum Computing. We are mostly a software company based in the UK, but we have also sites in other locations. And we're involved in lots of different areas of quantum technology. But what I'm going to focus on for my talk today is the issue of compiling software for quantum computers, which is a major area of activity for my group. So I don't think Oliver said this during his talk, but the era of quantum technology that we live in today is often called the NISQ era. So NISQ is an acronym invented by John Preskill a few years ago. It stands for Noisy Intermediate Scale Quantum. And that's basically talking about quantum computers with, let's say, 50 qubits, maybe more, maybe 100 qubits, but that's too few for error correction. And that the operations of these computers and oftentimes the qubits themselves are quite noisy. And because we have no error correction, we have to deal with this noise. So here is an example of a current quantum computer. I'm sure many of you have dabbled in quantum computing, have actually used this machine. It's our old friend, IBM Melbourne. And this illustrates a few of the pertinent features of NISQ machines. Now this one only has 14 qubits, so it's technically not at the level of a NISQ machine, but we'll just ignore that for now. So if you look down to the bottom right of the display here, you'll see this list of gates, which are the individual operations that this computer is capable of doing. And I won't go into the details of what these are, but these are a universal set of unitary operations. The first few of them act on 1 qubit, and the CX gate acts on 2 qubits. And if you're slightly above that, you can see the error rates, which you may expect. So all the operations here attract some probability of going wrong in some way or another. And if you look now at the top part, you can see the layout of the machine. So each circle corresponds to a qubit, and the color again shows the error rate associated with the operations of that qubit. And the edges in the graph show the places where you can do a 2-qubit operation. And so you can't do, for example, an operation between qubit 0 and qubit 3 because they're not adjacent in this graph. And so if we want to do anything with NISQ computers, we have to handle all of these issues. The issue of what gates does the machine have, probably not the ones that we wanted. What's the connectivity of the qubits? And most importantly, how do we manage the error rate? Oops, why am I not advancing? Okay. So one of the implications of having this high error rate is that a lot of the algorithms you might read about in your textbook are not really practical. A good example of this is what's called phase estimation. So in phase estimation, we're trying to extract some piece of data from the quantum state. So that's indicated by psi in the bottom of this circuit here. Now, in this example circuit, it doesn't really matter what these blue elements are, but they're extracting the phase information from psi. And that's going to give me the first 3 bits of my observable. If I want 1 more bit, I have to add a new circuit, a new larger circuit at the bottom to extract the 4th bit. And if I want 1 more bit of information, I have to extract an even larger one. And basically, for each extra bit of precision with this algorithm, I have to double my circuit depth. And the doubling of this circuit depth implies that I'm going to accumulate more noise. And since all of my operations incur noise, the longer my computation goes, the more likely I am to have nothing but noise at the end of it. So this kind of algorithm, this will not work on this machine. We have to do something else. And the thing which we do is typically called a hybrid algorithm. And it looks something like this. I have a quantum part where I prepare a certain state and I measure it. And I do many iterations of preparation and measurement, possibly with different iterations. I take all the results of those separate computations, I combine them to compute some quantity that I care about, and then I go back to my original circuit and I change some of the parameters to try and obtain a better estimate of that quantity. And I just go around this loop until I've minimized the quantity E, which I cared about. Okay, so that's what a typical algorithm looks like for a NISQ computer. So in order to help people write software like this, we've created a compiler, which is called pytket, and it works for many programming languages and many platforms of quantum computer. And it's specially designed to help you use NISQ devices rather than some future error-corrected devices. So pytket is free for non-commercial use. So if you want to use it, you can type the Python command at the bottom of the page here and try it out for yourself. So I'll be brief on what it means to be a compiler. When we're writing programs, we like to use high-level languages so that we can express our algorithmic intent in terms which make sense to us and make sense for our problem. And that high-level program would be translated by the compiler into machine code which can actually run. And of course, every machine has its own version of machine code. And if you look inside the compiler, it's quite a complicated piece of equipment, has many stages and lots of interactions between the stages. But if you look at these stages more closely, you can see that the first few stages are mostly concerned with handling the programming language itself. And the last few stages are mostly concerned with handling the machine code for the particular machine that you're working with. And the parts in the middle don't really have much to do with either of those things. These intermediate phases are mostly concerned with the logical structure of the program. And that's where we do all kinds of interesting transformations to improve our program. And once you notice that these three parts are kind of independent of each other, then you can arrive at the design of a modern compiler, which I'm going to take the LLVM as the prototype of this. And in the LLVM system, if you want to add support for a new programming language, you just write this front part of the compiler and you connect it to the existing intermediate part. If you want to add support for a new hardware platform, you just write the back part of the compiler that actually generates the machine code, and it talks to the intermediate representation. So we stole this concept to make tickets. And so when we say it's language agnostic, we mean that we can write software in the language of our choice, where that might be the low-level language called Chasm, something much more fancy like the functional language Quipper, or a huge number of different versions of Python. So Qiskit was mentioned in Oliver's talk, which is of course a Python framework, and many, many other frameworks are in Python for doing quantum computing. And we can accept input from any of these places, and Ticket can then generate code which can be executed on a wide range of different platforms. In a little bit more detail, it looks like this. We have a C++ core, and everything is wrapped around in Python. And so the front ends and the back ends, which deal with the translation, are written in Python. And so when you download it, you get this pytket Python library, and there's optional extensions. So you can use pytket with Qiskit, for example, if you want to use an IBM computer, but you want to write your software using Quill. So you could download the PyQuil extension and the Qiskit extension, and then combine them to generate code for IBM using Quill. There's lots of more things that I don't really have time to talk about, but it's all available online, so I encourage you to go and look at it. So you can use whatever you want to write the program, and you can run your program wherever you want to run it. What's happening inside the box is a very powerful and efficient optimizing circuit compiler. It does the layout of the circuit on the qubits, where that's important. We support symbolic circuits, which is very important for variational algorithms, because I want to replace parameters at runtime with new values. And we can also use the error rates, which the device reports about itself, to improve the overall performance, try and avoid, for example, if there's one link which has got a very high error rate today, then we'll try to avoid using that one in the computation. So here's an example of the Python code. I won't go through it, but I want to highlight just this line 5. So in all of this program here, this is the only line which specifies what computer is going to run this program. And if I wanted to run it on a different computer, I would just change this line and everything else would work fine. So what is happening internally is that we have some front end, let's just say it's Python, which is generating a very primitive description of the circuit. And then we feed this into our optimization routine, which can do a lot of different transformations to it. And then this emits a circuit or some other abstract description of the computation to a later phase, which knows about the architecture of the computer. And that phase then does what we call placement and routing. So it maps the circuit you wanted onto the shape of the computer. And then we do a final cleanup pass of optimization, again, with knowledge of the architecture before we send that for execution. And the thing which is actually sent off for execution, we call the kernel, in analogy with GPU programming. And that kernel is, of course, living inside this bigger hybrid algorithm in almost all cases. One thing that's worth noting is that at CQC, we're also making application software, for example, for chemistry. So we can use the knowledge we have of the algorithm that we're trying to do to devise special purpose optimization passes for those kinds of circuits. And I'll come to that later. Yeah, I have some charts showing that our compiler is very good, but I think I will just say that it's very good and leave it at that. There's only one point which I wanted to highlight here, which is this one. So this is a particular particular set of benchmarks we've devised for testing the performance of different software on very deep circuits of the kind that you might find in some kinds of chemistry simulations. And the green track is tickets of performance. So along the bottom is the size of the input circuit, along the y-axis is the size of the output circuit. So smaller is better. So you can see in this one, we're actually doing worse than everyone else. But we have in the brown trace is also a ticket pass specially designed for chemistry. And because we have the knowledge of what chemistry circuits are like, we can put in these kinds of specialist passes to optimize those things. Okay, so in his talk, Oliver did introduce the idea of circuits, but I want to go into it a little bit more before I press on to the details here. So a circuit, you might have seen in various pictures like this one in your textbooks. So a circuit is a way of describing which unitary operations are applied to which qubits. So each horizontal rail in this diagram is a qubit, and each box or linked box is a gate. And the gate can act on one or many qubits. And what this really is a notation to describe a unitary operation, which is, say, a matrix. And so there's many different ways of presenting the same matrix in circuit notation. But because we care about things like the noise, like the amount of time it takes for the circuit to run, circuits which denote the same matrix might actually have very different properties when you run them. And so the point of circuit rewriting or circuit optimization is to say that I'm going to prefer a certain kind of circuit, for example, one with fewer CNOT gates or one with a lower depth, and say that's going to be better than the equivalent circuit, which has more on some other metric. And so we do this in Ticket by using rewriting and equational theories. So here's a very simple example of a rewriting system. So if I look to the left, you can see some very simple rules. For example, if I apply the Pauli Z gate twice, that's the same as doing nothing. So if I receive ZZ in my circuit, I should just replace it with a wire. On the right-hand side, you can see if I do 3 CNOT gates in this contrapositive orientation, that's equivalent to doing a swap gate. So if I see 3 CNOTs like this, I might want to replace them with a swap. And so this set of rules is very simple and not very powerful. It at least has the property that it will terminate, but you won't, depending where you start from, you might not always end up with the same finishing position, depending on the choices that you make during the rewriting. So it requires some care to design a rewrite strategy which will actually reduce the size of your circuit in the best way. Thinking a bit more mathematically, what is a circuit? It's what we call a monoidal category, and we can use a lot of mathematics from category theory to try and simplify circuits. And in particular, by not working with the usual circuit notation, we can change to different ways of thinking about the same ideas. So all we require is that whatever notation we're using, we know what it means in terms of linear algebra, and we know how eventually to turn it into gates which our computer can do. So here's an alternative presentation of linear algebra. This is called ZX calculus. I'm not going to go through any of the rules of this. I just want to show it to you so you can see that it's very different to what you see in circuits. The operations have many ins and many outs. But this can do everything that you can do with linear algebra. And so because it's a completely different algebraic theory, we have different theorems, and so we can do different simplifications. I'm going to show some examples of this later. So what do we have in terms of circuits? We can do lots of rewriting. If we find something which is Clifford, we can synthesize an optimal Clifford circuit from small sizes. We can use ZX calculus. We can use symbols. We can use specific simplifications designed for electron structure problems. So here's an example of a circuit that we might use to prepare a hydrogen atom. So this is used in electron structure calculation. This is called the unitary coupled cluster ansatz. And you can see that it's quite large. This is one circuit on 4 qubits that I had to break into 3 pieces to fit on the screen. It's about 83 gates deep. And if you look at this, you will see that there is a very obvious repeating structure. And we can recognize the structure and use that to simplify the circuit. And I'm going to use it, take a little detour through ZX calculus to give an idea of why that would be interesting. So here is the repeating element. And if I just translate that, I get the equivalent thing below, which is just different notation for the same thing. But because in the ZX language I have different equational rules, I can simplify this. And I can do a bunch of transformations. And now I have what I call a gadget. This one is a phase gadget. So this is a large multi-area operation, which is applying to all four things, but it's equivalent to the subcircuit above. And in the more normal mathematical notation, this denotes the exponentiated Pauli Z operator that you see in the equation here. And this can be generalized using this other notation to account for any other exponentiated Pauli operator. So I don't know if anyone here actually does much work in computational chemistry, but these are extremely common operators in that area. And so these gadgets are very useful for computational chemistry. There's a big rewrite theory of equations for these things. I will not go through the details, but the point is, if I have two gadgets which have the same Pauli element on each wire, so if you look at these ones, you can see that on the top wire and on the middle wire, the color of the boxes is the same. And when that happens, I know that they're operating in the same basis, and so I can actually simplify the circuit down to something which is smaller than you would get if you just did this naively. And by applying a bunch of simplifications like that, we can achieve fairly significant reductions in the circuit size for these example chemistry calculations. So looking at about more than 50% reduction on average. So that's something we might want to do with circuits. So if you remember what we said earlier, less gates, less noise, more accuracy, right? But we have, as well as that, we have to also solve the problem called routing. And so here is, in a nutshell, what the problem is. If I look at this particular circuit, and I look at the qubit labeled S0, I can see that this qubit is actually interacting with all of the other 4 qubits in this circuit. And if I wanted to run this on our dear friend IBM Melbourne, I can't actually find any vertex in that graph with 4 neighbors. So as it's written, that circuit can't be run on this computer. So the problem of routing then is to make it fit. So we start off with a circuit which we want to run, and we have an undirected graph which we call an architecture. And the architecture is just which qubits are connected to which qubits. And then the problem of routing is to find a way to get an interaction which is not possible in the graph to become possible. And we do this by inserting swaps into the circuit. So the effect of a swap is basically to exchange 2 qubits. And as you can see from my equation here, a swap gate requires 3 CNOT gates and 2 Hadamard gates. So that is quite an expensive little subcircuit. So we don't want to do that if we can avoid it. So finding the optimal solution to this problem is NP-hard, and that's just to do it across one time step. If you want to do it across the entire depth of the circuit, that's much more difficult. There is a lower bound result, which says that in the worst case, or worst best case, I can never remember which way around it is, we should expect a log n increase in the depth. You can not expect to do better than that in general. Okay, and so what we get in the end, so we start with our circuit and we map it to a routed circuit. So notice that I have to take my 6 qubits of my logical circuit and I have to map them to 6 available qubits of my architecture. And so I get to decide freely which 6 they are. And I will try to do this to minimize the number of swaps that I have to do. And then I'll produce a routed circuit, which, as you can see, now has some extra swap gates added into it. And then at the end, I'll have a final placement of the qubits, because I don't have to leave them in the same place for the whole circuit, right? I can obviously move them around as long as I remember where they are as I go through my calculation. So the solution that we use in Ticket for this problem is to cut the circuit into time steps and use the heuristic to put to choose where to put which gates can be done immediately and then reslice as you go ahead. And we use small amount of look ahead to do this, but it's not particularly deep. So this is very fast, and it can handle very large circuits up to 500,000 gates with no problems at all. The chance of you being able to run a computation with 500,000 gates on a NISQ machine is basically zero, because you will accumulate too much noise by then. And we can compare ourselves to Pytket, which is one of the few systems which also can do this quite well. And you can see that Pytket is significantly outperforming Pytket in these examples. And in general, so on the Melbourne device, which is 15 qubits on the day we did this test, we're getting an overhead multiplicatively about 1.5 versus Pytket of 2.24. And similarly for the Singapore architecture. Okay, so let's look at this picture again. The key word of NISQ is noise. And in everything I said so far, we didn't take into account this noise, which is something we really ought to do to get good results. And with the way that we do this using Pytket is we try to make sure the initial placement of the circuit on the architecture is in the least error-prone part of the computer. And thereafter, we could use the noise information to inform the routing algorithm. Our experiments have shown it makes very little difference at all. So it's mostly due to choosing, most of the improvement you can obtain is by choosing well where to put your initial qubits. So here you can see 3 different plots. So the y-axis here is the Jensen-Shannon divergence from an ideal simulated circuit. And so lower is better. And you can see that in the case where we do no particular placement, just whatever the circuit was by default, the divergence goes up very rapidly with the gate count. GP stands for graph placement. That's our usual algorithm where we try to find the largest subgraph which can be fitted onto the architecture without any swaps. And then we could improve graph placement by adding noise awareness. And that is the purple trace. And we can see that if we are sufficiently careful in choosing our placement with knowledge of the noise in the device, then we can basically gain, for the same level of Jensen-Shannon divergence, we can almost double the depth of this, or more than double the depth of the circuit, depending what you compare against. And more, I'm not going to go into any more details about how to control noise, but it's the major topic of research in this area at the moment. Anupam, how much time do I have left?
Yes, sure.
Okay, so I will just go briefly into one thing. So everything I've said so far assumes that you already have a circuit. But unless you're a quantum computing researcher, you probably don't care about quantum circuits at all. You care about something else that you want to compute using your quantum computer. For example, our friends in the quantum chemistry world, they care about the structure of the electrons in the molecule they're trying to simulate. And they would much rather express their program in terms of these higher level concepts and not have to translate it down into circuits. And if we think about the hybrid algorithms that I showed you at the beginning, and we look a bit closer at what is happening here, this part is the only part which actually runs on the quantum computer. And this pink box here, we call the ansatz. So this is the circuit that prepares a state which we want to measure. And there are basically 2 kinds of these ansatz. One, which is what we call physically motivated, for example, unitary coupled cluster. And these are very nice in the sense they will probably converge. They are basically informed by the physics of the system that they're simulating. But the bad news about them is they tend to be very deep, which means for NISQ machines, if we accumulate too much noise, then we have no chance to actually get a useful answer at the end. The other big class of ansatz are the hardware efficient kind. Now, hardware efficient ANSYS that have problems of convergence. In particular, they feel what's known as the barren plateau problem quite badly, and they don't have any relevance to the structure at hand. It's just a completely generic form of circuit derived from the machine, not from the problem. So the advantage of this is that they have very shallow circuits. So the question is, can we combine the benefits of the physically motivated kind with the hardware efficient kind? And we do this by looking slightly higher up into the stack. So this is on the left here is the state we'd like to prepare, the trial state of what's called UCC ansatz, and you can see that it's achieved by starting with this phi0 state, which is a very simple initial trial state, and applying a unitary operation to it, which depends on t. It doesn't matter what t is right now. And the operator itself has this particular form of being an exponentiated sum of Pauli's. So if we are being very clever here, we know that this is the thing that we care about, we can think about generating the circuit directly from this. So the way that we do this is that we divide these Pauli terms into sets which commute, and then everything in this commuting set will be simultaneously diagonalizable. So that's what we do. We diagonalize them all at once, and then these diagonal exponentials can then be synthesized using phase polynomials. And I will not have time to talk about phase polynomials, but it's a fairly well-known technique. And so if we compare the results that you get from starting at the higher level and using your knowledge of the problem structure versus what you would get by going naively from the problem to circuits, then you can achieve almost an order of magnitude improvement in the depth of your circuit. And if you've improved the depth of your circuit, you've also improved the accuracy of your calculation. We did achieve, in the best case, depth reduction of 90%, which is definitely the difference between having something which is at least potentially accurate and something which is definitely not accurate. So you can read a bit more about this at the archive number shown there. And my collaborator, Alex Cowton, gave a presentation about this at the International Quantum Compilers Workshop earlier this year. I have more, but I think I'm going to stop there and then just go to the end. Oops. And just invite everyone to try the software out for yourself. If you find any problems, let us know about it. As I mentioned earlier, it's interoperable with pretty much everything you can imagine. So thanks for listening.
Yeah, thank you, Ross, for the engaging and interesting presentation. So now the floor is open for questions from the audience. If you have anything to ask, please. Okay, maybe I will start discussion with a general question. So how do you perceive the different tools like keynote, pytket, and there is also recently one released from this group in Waterloo called Stack. So there are open source tools and there are proprietary tools, and this is in the early stage of quantum EDA. And there are probably many in-house tools as well. So how do you see pytket positioning itself? So it's a very general, non-technical question.
Yeah, so in comparison with Qiskit, I mean, as Oliver mentioned in his talk, Qiskit has a very broad ambition to be a framework which can adapt itself to more or less anything, and especially as a playground for researchers to try out things. pytket is basically trying to provide the best possible implementations for a lot of the hard tasks that anyone doing quantum computing would have to handle. So if I'm someone who wants to try out some new algorithms, is it really necessary for me to learn all about how to optimize circuits to get them to work? I think it should not be. And so the point of pytket is to take that problem away and leave you to worry about your actual problem, not the problem of programming a quantum computer. Okay.
And one question regarding the part where you were explaining the routing. Mm-hmm. You mentioned about the log-n depth increase. That is for the linear nearest neighbor circuits, or it's for general circuits? So I'm not very sure about that.
Yes, so I can make that statement more precise. So the assumption is that the circuits are random, so they don't have any fixed connectivity, and that the architecture you're mapping them onto is a random for regular graph.
Okay. Okay.
So it's an asymptotic statement in this stochastic regime.
Okay.
But in the case of specific architectures, I'm not sure what the best known results are.
Okay. There is also some recent algorithms which are advocating not using swaps, but using a constant Gaussian elimination by using a Steiner tree. So do you have some comparison with that?
Yes, so in fact, we use some of these techniques in our system for the synthesis of these larger units. Okay. So basically, the thing that you should do is you should start with the highest level logical component and then synthesize a circuit onto the shape that you already know it has to be. And so these algorithms based on Steiner trees are doing that. They're synthesizing a higher level construct for the architecture.
Okay.
And in an ideal world, that would always work perfectly. But when it doesn't work, then you can fall back to routing to insert swaps. And I'm explaining more the simple version here where we're just going to insert swaps. But there are other more complex ways to move qubits around. For example, there's a relatively simple thing called the bridge gate. So if you need to make a qubit jump over another qubit, then you can
Right.
Okay. Of course, in some architectures, like IBM, for example, the 2-qubit gate is CNOT. So you have to synthesize swaps out of CNOTs. In ion trap systems, it's not an issue because they just physically move the ions into the right place and then they can apply whatever gates they need to do.
Okay.
So in those kinds of systems, swaps are almost noiseless, but they actually take a very long time on the wall clock compared to other gates.
Okay. Yes, here is a question from Jim Chan. Is asking if the high-level code compiles directly into the circuit for the specific architecture.
No, that is part of our general concept with Ticket. So what we do is we have our own internal representation, which is very flexible and can accommodate all these other formats like the Pauli gadgets and the ZX terms and whatever other interesting representations that could be useful for circuit transformation. And only at the very end where do we try to generate the gates for that particular machine. And we have a different code generation for each gate set.
Okay. And another general question from the EDA community might be that whether you are allowing people to develop some code and integrate with Ticket, or it is just a university license and we can use it as a software tool.
At the moment, it is closed source. We are extending the API to make it a bit easier for people to write their own optimization passes.
Okay.
But since it's a C++ program at heart, it's not very beginner friendly. But the Python interface is a bit easier to program. But
okay.
It's something we're working towards.
Okay. Any further questions from the audience? If not, then let me thank on behalf of the audience to Ross again. So please stay by and we will continue with the panel at the end of the talks. Okay. Thank you very much.
Thanks for listening. Cheers.
Yeah. Okay, now we move to our third and final speaker for today, Dr. Robert Wille. Robert, you're already here, right?
I'm here. Hello, Anupam.
Yeah. Hi. Hi, Robert. Yeah. So Robert Wille is a full professor at Johannes Kepler University, Linz, Austria, and is also a chief scientific officer at the Software Competence Center, Hagenberg, Austria. He received his diploma and doctoral engineering degree in computer science from the University of Bremen in Germany in 2006 and 2009, respectively. Since then, he worked at the University of Bremen, at the German Research Center for Artificial Intelligence, the University of Applied Science of Bremen, the University of Potsdam, and Technical University of Dresden. Since 2015, he is working in Linz and Hagenberg. His research interests are in the design of circuits and systems for both conventional and emerging technologies. In these areas, he's published more than 300 papers in journals and conferences and served in editorial boards and program committees of numerous journals and conferences. For his research, he is frequently awarded with like a Best Paper Award in ICCAD, DAC Under 40 Innovator Award, and a Google Research Award, and more. So thanks, Robert, for joining us, and we're looking forward to your presentation.
Yeah, thank you very much, Anupam, for a nice introduction. Just to double check, you can hear me and you can see my slides, and ideally me as well.
Yes, perfect.
Perfect. Then thanks a lot for having me. Thank you very much for the invitation. I did my talk in a more general fashion, saying design automation for quantum computing, and the main idea is a little bit to make quantum computing, or my kind of mission is a little bit to address design automation experts who haven't worked on quantum computing yet, and to showcase a little bit how design automation expertise and background can be helpful for the quantum computing domain. And so that in order to make a point that quantum computing can be an exciting and interesting playing field for design automation experts, and that you with design automation expertise you indeed can make a nice impact in quantum computing. So this is basically what this talk is about. And in order to start this talk, I start probably with something which you already have heard, and which you basically have heard in the previous talk, namely about talking about this impressive success quantum computing has accomplished in the past years, and the momentum quantum computing quite have currently. You probably have heard all of that. You have seen that you have heard, you know, that we have quantum computers by IBM, by Google, by Rigetti. I was really impressed with the announcement a couple of weeks ago of IBM's roadmap. I mean, they even dare to say that in the future they're gonna have millions of qubits. I'm not sure how realistic that is, but I like very much the kind of ambition which is behind this kind of announcement. Because when I started working on quantum computing 10, 15 years ago, I was still this crazy guy who does these kind of weird things. I did my PhD a little bit on those topics, and everybody was asking, is this really a thing? And now having seen serious companies claiming, okay, in the future we're gonna have millions of qubits, and they're gonna this technology is used for practically relevant applications. I think that's a really nice thing. And the reason why I'm bringing this up here is not in order to give you the third introduction on quantum computing, but actually to compare that with the development of conventional computers, because you can actually see in the development of quantum computers, for example, here with respect to quantum volume and the existing computers we have so far, you can see a lot of similarities. In fact, also in the conventional world, the first computers were rather bulky. And also, we all know we have this Moore's law and this exponential development of the technology. We see a similar thing with the quantum volume, with the development of the number of qubits, as shown by this IBM announcement. And overall, I think this is interesting to see that how the technology evolved. And then at some point that had happened in the conventional realm, and in my opinion, that we can now see that very nicely in the quantum computing realm as well. I think Ross's talk was a perfect example for that, that we're now seeing that, okay, we now also need tools and methods and software which allow us to really make the best use of all of this technology. And in the conventional realm, I think it basically we can say for sure that EDA tools are an important pillar which allowed or which enabled the success of conventional realms. Without sophisticated and efficient EDA tools, we wouldn't have computers and smartphones and all these kind of technologies so far. And those tools, they can handle enormous complexity. And on top of that, we not only have those tools, but we also came up with very powerful and efficient design or compilation flows, not flaws, but flows. This is exactly now what we also need for the quantum realm. And I like this analogy a lot, because many years, and it makes perfect sense, but many years, the physics part of quantum computing were the dominating factor, and it probably still is. But more and more we learn that computer science, the design automation, is actually becoming a real important issue. And TCAT is a perfect example of that, and is a perfect example of the development of the recent recent years we have seen. So tools like TCAT, as introduced by Ross in the previous talk, are really essential in order to keep going on the development of quantum computing. But of course, there are several challenges which need to be addressed. So developing tools for quantum computing differs from developing tools for conventional circuits, and the whole way how we are programming is totally different. We have a completely different paradigm. One is probably not the most important thing, but one certain example is, of course, that the way how you conduct operations is different. So everything in quantum computing, as you know, is reversible. That means in conventional realm, we can multiply 4 and 5, and then we get 20, but we never can, when I just have the output 20, I never can uniquely determine the input again. Of course, it could be 4 and 5 again, but it could be 2 and 10. In quantum computing, this is not allowed. You need purely reversible computations. And this is just one example of how different the paradigms are. And of course, not to mention that in quantum computing, we have to deal with superposition, so we have to deal with being 0 and 1 at the same time. We have to understand the quantum operations, obviously, in addition, is much more intuitive to us than, let's say, in Hadamard operation or in T-gate operation. We have physical constraints which need to be satisfied. Was also talking about that. We have error correcting to deal with, and lots of other issues which turned up in quantum computing and never really was such an issue in the conventional realm. And another problem on all that is that on top of that, we have a substantially larger complexity in all the design tasks we're tackling. As you all know, as experts in the design automation realm, in design automation, we are used to very very hard problems with respect to complexity, and so we are not afraid of complex problems. However, in the quantum domain, actually many problems have an even harder complexity, and I would like to briefly illustrate that with the example of a simulation here. Simulation in the conventional realm is actually rather easy. You have a circuit like that, you have an input assignment, and then you simply simulate the corresponding signal values as shown here. In the quantum realm, even some presumably simple tasks such as simulation suddenly becomes more complex, because in quantum computing you don't work with Boolean values anymore. Instead, you have to deal with these superpositions and stuff. And this is basically conducted by having exponentially large representations for single quantum states. And just by this, you can already see a simulation, a linear problem in the conventional realm suddenly becomes an exponential problem in quantum computing. And those are just some sort of examples on the challenges we need to face here. And in the following, in my talk and in the following, I don't know what time is left, 10, 15, 20 minutes, I would like to provide you with some examples how design automation expertise can help in order to tackle these problems. And I would like to continue exactly with this example of simulation, because simulation is a very nice example to illustrate, on the one hand side, the complexity we have to deal with, and on the other side, it's a nice example because I hope I can explain to design automation experts like you in very brief time how we as design automation experts can make a difference here. Because the nice thing on simulation, at least when we talk about perfect simulation, so not considering noise or error aspects, those are issues which are also important, but which I will ignore here for the sake of my argument. The really nice thing on simulation and quantum computing is you don't have to become a quantum physicist or a quantum expert, because simulation in quantum computing is basically just matrix vector multiplication, whereby the vectors represent the state of a qubit and the matrices represent corresponding operations. And as an example, if I have, for example, in basic state 1 in my quantum system, so this is a qubit which has the value 1, and I have a Hadamard operation which I would like to apply to this state. And Hadamard operation is a special quantum operation which is defined by this matrix here. You don't have to be a quantum expert. All you have to do is you have to understand, okay, I have a quantum operation, this Hadamard, this H operation here. This quantum operation, for some reasons, there's a reason behind it, but you don't have to understand all that. You just have to accept this operation is defined by this matrix here. And your quantum state 1 is defined by this matrix here. This is the amplitude for the Boolean basis state 0. This is the amplitude for the Boolean value basis state 1. And since we're talking about a 1, you have a 0 here, a 1 there. And once you've got that, the simulation is basically just matrix vector multiplication. That means you multiply 1 times 0, which is 0, plus 1 times 1, which is 1. So you end up with this 1 here. And then you multiply 1. You multiply this one with this 0, which is 0 again, and then you multiply -1, -1, and then you end up with this one here. And this is the result of your of your operation when you apply a basic state 1 to a Hadamard operation. So basically, if you want to write a simulator for quantum computing, you simply need a matrix vector multiplication method. And the problem right now is, of course, that those matrices and state vectors, as I mentioned before, they are exponentially large. So this is the main challenge to address that. So how can we conduct these operations in a more compact fashion? And again, design automation can help here, because one way in which we in the past tackled exponential complexity is by doing that through decision diagrams. And we can actually employ similar schemes here as well. And I would like to illustrate that with this matrix here. So this is a matrix, obviously a larger matrix, representing, in this case, a 3-qubit operation. So this is a matrix of size 8 times 8. This is exactly the representation for a 3-qubit system, because 3 qubits means you have to represent that with 2 to the power of 3 times 2 to the power of 3 matrices. That's what we have here. And of course, this would be an exponentially large representation. However, with decision diagrams, you can represent that in a much more compact fashion. And this is done by actually building up a decision diagram, which decomposes your overall matrix into submatrices. And this is highlighted a little bit here by these blue lines, because what's basically now happening is we're simply saying, okay, you decompose your overall matrix into a first submatrix, into a second submatrix, into a third, and into a fourth. This is the first, the second, the third, and the fourth. You can basically check that. That's the fourth matrix, which is actually shown here. And by decomposing like that, as I will show in the following, now you can actually find potential for a more compact representation. As an example, for example, if you check out these two matrices, what you can do in the first step is you can actually factor out some constants in here, which will look like that. So all I basically did here right now is I took this constant here, which is basically a constant which is happening here. No, I'm sorry, what you don't factor out. I'm sorry. What I basically did is I don't factor out anything here right now. What I did so far is only I recognized that these two matrices are identical. Right? If you compare them, they are completely identical. So I don't have to store them twice. It's completely sufficient to store them only once. And this is what's happening here. And then another way is, and that's not what's actually happening, is that in another way you can now start factoring a value out. For example, you see all those entries here, they have the same factor in it. And when I multiply that out, I can actually just annotate it on these edges, and I can still get a representation which only argues over ones and minus ones and has these edge weights here. In a similar fashion, I can do that here as well, right? Because I go back, here you see, okay, also here you have a common factor. If I factor that out, I get basically this matrix. And then suddenly you can recognize by factoring this -1 out here, I suddenly get a matrix representation which is identical to this representation. So by just factoring it out, I suddenly get the same submatrices again, and that means I can share them as well. And just by these tricks, I hope you can see what I'm doing here right now. I'm exploiting redundancy, and by this, I'm getting a more compact representation rather than representing all submatrices or all entries separately. And if I do that in the following fashion, in the recursive fashion, so I would do this now for this matrix as well, which I again can split up into 1, 2, 3, 4 submatrices. So I can continue on that, upon that, and then I can continue utilizing this sharing. And by this overall, I eventually get a decision diagram representation as shown here, which overall is much more on, and this is the more compact representation here. And this is then basically a representation which still represents my entire matrix, but maybe when I was able to exploit these redundancies as I sketched it out, allows you to represent this whole thing in a much more compact fashion. And the argument is right now, there's no guarantee that you always end up with a non-exponential representation. So in the worst case, you still end up with an exponential representation. So in the worst case, you don't win anything. But in many cases, and hopefully in many practically relevant cases, you get an improvement. And this is a nice example where design automation expertise can help. And I'm not showing that in much detail, but bottom line is that you can now utilize this. You can now utilize that for simulation, because in a similar fashion as I represented matrices here, in a similar fashion you can also represent states, and you can conduct matrix vector multiplication with that. I don't want to go into much detail due to time constraints, but this is basically one way of what you can do. All right. My slides are actually very slow here. I'm not sure what's the problem, but anyway. And I'm just very quickly showing what kind of impact this can have. In fact, we conducted some experiments, and as said, in many cases, we are not able to have an improvement. Sometimes decision diagrams even get worse, but some selective results really show that within conventional simulator, you sometimes, which relies on a vector matrix representation, you sometimes end up with a huge amount of main memory which you need, while for other, while with using decision diagrams, you just get a fraction out of that. And for some selective results, we can actually solve problems substantially faster than with vector matrix representations. So there's one experiment I particularly like that we have cases where a simulation of the Shor algorithm, for example, requires 30 days on a supercomputer, while with decision diagrams, we were able to do this in a minute only. And this kind of shows a little bit the kind of impact decision diagrams and by this design automation expertise can have. It is not, again, that's important to say, it's not a solution for everything, but it's a perfect and, in my opinion, really neat alternative to matrix vector representations or tensor products or alternatives. It's sometimes better, and it, by this, constitutes a nice complementary solution. Another issue where design automation expertise can help, obviously, is compilation. I don't want to get too much in detail into that because basically Ross covered that quite nicely in his previous talk. I just want to make a brief statement here. You know, compilation is basically you've got your original conceptual algorithm, you've got the target device, the target architecture, which has a limited gate set, and then your first step is to realize your conceptual algorithm in a fashion which is composed of gates, composed of this limited gate set only, which is synthesis or compilation. And then the next thing is you have to deal with this limited connectivity. So you have to map your logical qubits here to the physical qubits of your architectures, which may end up into solutions like that, where you then suddenly recognize that some gate does not satisfy your connectivity constraints. Because of that, you have to add, for example, swap gates or other solutions, and then you get the resulting problem. Basically, stuff or issues which have been covered before. And this is one thing you have to do. And then you have limited fidelity. So you want, of course, you have to have your circuit as compact as possible. And in many cases, you have potential for optimization. So all the gates which are highlighted here actually can be either canceled, like in this case, or can be reduced. And then you get a smaller realization. And I run through all that, not in order to discuss any details and in order to, you know, introduce a new method. Ross did a much better job than that before. I just want to make the statement here that all those problems we are seeing here, and many of these problems we are seeing here, are basically typical, kind of, in my opinion, typical EDA problems, in the sense that, for example, this swap insertion here, in order to satisfy the connectivity constraints, this is actually just a structural combinatorial problem. In fact, it's an NP-hard problem, has been proven as NP-hard, and it's a typical optimization problem, how to map the qubits to particular locations, and then how to map them in a fashion so that you need the least amount of swap gates, for example, or in order to get the best fidelity. And all I'm saying, what I want to say here is, if you think quantum computing sounds interesting, but you don't have the expertise and you would like to do something in this world, all I want to say here is a little bit that just give it a try, because many of the design problems we're having here, like this sort of a mapping problem here, can actually be tackled by experts from design automation without having a much much insight into quantum computing. It certainly doesn't hurt to have insight in quantum computing, but many of the problem, I'm not saying you should completely ignore that. I'm just saying in order to really solve the problem, if you have a stakeholder who tells you what constraints are important, you still can make an impact. And all I'm saying here is we should get much more people from the EDA community involved in quantum computing, and it is not as scary as it might look in the first glance. And because many of the problems are very typical to problems which we usually have in our design automation realm anyway. Last example which I would like to use here to illustrate where design automation for quantum computing can help is verification, originally motivated by the compilation flow as well. In a compilation flow, you have an original circuit and you compile it down to a circuit composed of elementary gates, for example. And then, of course, you would like to know whether or not both circuits are still functionally equivalent. One easy way to do that is you simply take all the matrices of your gates, you multiply them together, get your overall matrix representing the entire circuit. You do the same with the other circuit, you multiply all the matrices of the gates together, get a resulting matrix, and if both matrices are equivalent or basically the same, you have proven that both of your circuits are functionally equivalent as well. And design automation, and then the problem here again, those matrices are exponentially large, so this is a complex problem. And here design automation can help as well. In fact, I already introduced decision diagrams. So one simple thing you could do is you can simply generate a decision diagram representing this circuit here. You can generate this decision diagram representing this circuit. And since these decision diagrams exploit redundancy, in case both circuits are functionally equivalent, the decision diagrams need to will be equivalent as well, and then this actual process will actually look like that. And all you have to check is basically just whether or not your pointers referring to the corresponding representation for this circuit and that circuit point to the same root node, and then you have proven that both circuits are equivalent. However, all that of course only works nicely if also the decision diagram is compact. And as I said before, decision diagrams, they may offer a more compact representation, but they are not guaranteeing it. And in fact, there might be many cases where in where a quantum circuit will still yield a decision diagram which is too large, so that you run into memory explosion problems. And here is another thing which I would like to pitch a very nice characteristic in quantum computing, which we can exploit as design automation expert and which we weren't able to exploit in the conventional realm, and which I personally find very interesting. In fact, we can exploit this particular characteristics of circuits. I mentioned before, every quantum circuit is reversible, and because of that, we can conclude the following. If circuit G and circuit G prime are equivalent, then I can easily take the inverse of my second circuit, and if I then concatenate that with the original circuit, if both are equivalent, then the concatenation of the inverse of the one circuit with the other circuit should yield the identity. And this is a very interesting property, and property which is already known for quite a while. And now I would like to showcase how nicely you can utilize this property in verification using decision diagrams. Because what you could do is you could take your decision, you can take your circuits, you inverse one of these circuits, which is easy because an inverse of one circuit is simply flipping all the order of the gates and inverting each single gate. So this is no problem at all. We are inversing this first gate here, and then we concatenating it with the other circuit. And if then the identity results, we are fine. And now the good news is in a decision diagram, the identity representation is linear. That means representing the identity does not cost us anything. Basically, it's linear with respect to the number of qubits. So this is actually very intriguing to do. The only problem we have here right now is that in order to get this identity, again, I have to multiply all those gates together. And this means to some extent, if I do this for the gates of the first circuit, of course, at this point here, I will end up with my potentially very large decision diagram. And if I then multiply the remaining gates and both circuits are equivalent, I eventually may end up with the identity, which is compact, but I may have intermediate result here, which is still exponentially large. So in this regard, just this idea doesn't bring me anything and any benefit, because I still will have an intermediate result which will have the original complexity. But now comes the catch. Now comes the nice thing. What you can do, you can actually do a slightly different scheme. You could actually start with the decision diagram of the identity, which is this representation here. And now you could basically say, okay, now I'm not multiplying all gates from this circuit first and then all gates from that circuit, but you could do in a fashion that you say, okay, you know what? I start with multiplying one gate from here, and then I get this decision diagram here, which is a little bit larger, but not blowing up already. And then I can multiply with the gate from this part here. And since those gates are the same, obviously I have to return to the identity again. And by doing this, I could do this now with the gate here and then with the gate there. And now I'm doing it with this gate here. And now if I would just apply a single gate here, I would not getting back to the identity, because obviously this is now a different realization. But just hypothetically, let us assume I now have an oracle which knows everything and which tells me now would be a good idea to multiply all those gates here, which realize this one gate. Then I would end up with the identity. Obviously, how to get this oracle will be a big question, but I would like to show you a little bit how you can utilize, if you have certain information, certain knowledge, how you can utilize that. Because what's happening here right now, I'm verifying that these two circuits are equivalent by multiplying one gate from this circuit with corresponding gates from the other. I don't know, my pointer is not really moving fast enough. So if I multiply one gate from here and one gate from there, and as I do this in a very particular fashion here again, one gate here and then one gate there, I always stay very close to my identity. And by this, I actually can realize, I can verify the equivalence of my two circuits in a very clever fashion. And now the question, of course, is, from where do I get this information, when to apply a gate from one side and when from the other side? For this, I need dedicated strategies. I have to exploit the knowledge about the relation between these two circuits. And here, maybe compilation results could help a lot, because as you know, we have a compilation result where we map, for example, this gate to a particular sequence of gates here, and then compilation results where you map qubits to it, where you add swap gates. And if you know what happens in your compilation results, you will be able to use that in the verification, because something like this relation here is really easy to incorporate into a verification flow. Other things like the swap gates here, you need to incorporate so that your matching with your qubits work at the end of the day. And just things like optimization, they still can be incorporated in such a verification flow, but probably not comprehensively, because optimizations might not be that easy to incorporate into verification. But just if you just use this information in order to derive a heuristic which comes close to how your verification strategy should look like in the best case, is one way to utilize this information here. And this is basically what I wanted to show here a little bit. And at the end of my talk, please don't mind if I do a very quick commercial, because all the methods I introduced here have also been, of course, implemented, and we actually made them all available in our GitHub repository. So you can download the code and you can use it on your own. However, one particular thing I would like to particularly pinpointing you through is that even if you want to give it a try but don't want to download some code and want to compile the code and so on, we also just recently launched a visualization tool, which you can see here. And in this visualization tool, what you can do, for example, you can simply load I don't know, in quantum algorithm like a Grover's algorithm here in Quasm, and then here on the right hand side you will see the corresponding decision diagram structure. And then by clicking on the buttons here, you can basically apply the H gate, the X gate, and you can basically check out how the corresponding decision diagram will look like. And you can do the same also even with the verification approach. So we basically did this here as well. And then you can basically load different algorithms. And then you can apply exactly the strategy, the verification strategy I showed before. You can apply a gate from one algorithm and check out the effect on the decision diagram, and then you apply the same from the other algorithm, and then you see you're ending up with the identity again or not. And long story short, you can play around with the methods I just described using this tool, the tool which is available on this web page here. And we did that a little bit in order to, in order to showcase a little bit how, and then to make it easy for people who want to get involved into quantum computing and design automation for quantum computing to provide some easy access way of playing around with things. And this basically brings me to the end of my talk. So the bottom line, and hopefully the main message, which hopefully arrived to all of you, is that, in my opinion, many of the design problems which we have to deal with in quantum computing are standard combinatorial problems for which we have the expertise to, for which EDA or computer-aided design CAD methods can very nicely be employed. I showcase that with the example of decision diagrams, where we basically can sort of have more efficient representations in terms of decision diagrams than in terms of vectors. What you can do is you can use these methods as black box. So even if you don't understand how these decision diagrams work internally, you still can download the package, and then you can say, okay, please give me a matrix representation of this quantum operation or that quantum operation and the matrix operation of this quantum state. You don't have to care about, you can load in a Quasar file, for example. You don't have to care about how the decision diagram work. You can still use it just as a black box and then exploit the benefits of decision diagrams, even if you don't understand that. And we also started integrating these kind of methods to tools in IBM and Google. So also here we see some benefit. And long story short, feel free, be open to it as design expert and use your expertise to solve the problems. More information on all the methods I described here are available on this web page. And I hope I did overtime or I stayed within my time limit, but this is kind of the message I wanted to convey. Design automation can really have an impact in quantum computing, and I would recommend give it a try. It is an exciting community, lots of momentum happening right now, and lots of stuff where design automation experts can really make a difference here, in my opinion. Thank you very much for the attention, and again, thanks for having me here today. Thank you.
Thank you, Robert, for your interesting coverage, specifically on the focus of verification, which I think is quite refreshing for many of the audience. So now I request the audience to ask a few questions to Robert. Maybe I begin with a question here. Since you pointed to this blow up of the decision diagrams in the case of this identity creation and equivalence checking. So did you manage to find some specific optimizations apart from the trick that you mentioned that you slowly add gates from both sides? Is there anything else that can be done to limit the size?
We're investigating this right now, and I'm getting encouraged by the fact how decision diagrams in the conventional realm turned out. So as you might know, in the conventional realm, we've got binary decision diagrams, which rely on Shannon decomposition and which are good for a particular class of functions. And then we have other types of decision diagrams which rely on different decomposition methods. And we haven't investigated that in detail yet, but we strongly believe that the way how you decompose your matrix or your vector most likely will have an effect on the size of the circuit. And right now we're really at the beginning in understanding the nature of decision diagrams for quantum computing. But I could imagine that in quantum computing, we probably will have, in the future, we probably will have different types, different decomposition methods for different classes of quantum, which work well for certain classes of quantum functionality and worse for other classes of quantum functionality. And the thing is, we are not only talking about the decomposition of matrices, but we also talk about, I talked about these edge weights, and here you have different ways of normalization strategies. So the way how you factor out values from your submatrix also is going to have an impact. The variable order, of course, is going to have an impact. So there are lots of, let's say, parameters we still can tune on, which eventually might yield to a smaller realization. At the representation, at the end of the day, of course, it's basically impossible that we end up with an representation which will always be compact. If we would find something like that, we would kill quantum computing, I guess, because then you wouldn't need a quantum computer anymore. So obviously we will reach limits at some point. The question is just how far we can push the limit above with different kinds of representation.
But you mostly focused on the equivalence checking part. And if I look into the general field of test and verification, do you think there are some other problems that's worth looking into, like online testing or test generation?
We do. In fact, test generation or stimuli generation or simulation is an interesting point, because recently we just sort of prove, let me put another way, in the conventional realm, we also have test generation and constraint-based verification and fuzzing approaches in order to check the correctness of a circuit, for example, but we all know they are kind of not complete. And the same kind of holds in quantum computing as well, but we actually found out that simulation is much more powerful in quantum computing than in the conventional realm, in the sense that if you have an error, if your two circuits are, for example, not equivalent, then we recognize, we have a proof that if there are certain classes of errors, a single pattern, a single simulation one can always show the error. And if you have multiple errors or certain other classes of errors, even then empirical, we've shown so far that with just a couple of simulation runs, in many cases, you have no guarantee, but in many cases, you will find the error. So what I'm trying to say is, in the conventional realm, when you do simulation, you often have masking effects, and you often have to simulate, you need to find the right patterns, and often it's impossible to verify the equivalence of two circuits just by simulation because of masking effects and everything. And in the quantum realm, all I'm saying is that it's interestingly much easier, just with a couple of dozens of simulation, of randomly chosen simulation patterns, you will be able to find errors. So even here, there's an interesting benefit. And it's all really fresh. We just have some proofs, some theorems out developed or proven, which show a little bit the difference, how easy it is to check for an error in the quantum realm compared to the conventional realm. We just started it. I'm pretty sure there's lots of potential to be explored here as well. I hope it makes sense what I'm saying.
Yeah. Here there was an interesting thing that you mentioned about the simulation. So I'm aware that simulating a quantum circuit classically is already hard, and it should soon become intractable for a complex quantum circuit. So when you meant this testing and simulation, is it a simulation on a quantum platform or simulation on classical?
That's exactly then the caveat again. Right now I'm talking about simulating on a conventional machine, and that's exactly the caveat here, that of course I'm saying using simulation in quantum computing is much more important, much more powerful than in the conventional realm, with respect to the number of with respect to how many stimuli you need to consider. But the simulation process itself, of course, is exponentially harder again. But indeed, what you suggest could maybe an interesting thing, that you want to check out whether or not your physical realization or your quantum algorithm on your physical machine is working correctly. And then maybe here few patterns will be sufficient. Some colleagues in the quantum community just a year ago or so published a paper on that, showing that, okay, you can actually check out whether or not your execution is correct with single or with very few patterns only. But it's exactly the point. When you want to check something on a conventional machine or on a physical machine makes a difference, of course.
Any questions from the audience?
This is Humberto. I may have a question, because I know Robert. We met each other several times over the last several years. I align very much with your message, which is still very consistent to how you were proclaiming it, let's say, several years ago. Because the focus should also be much more on making new applications, quantum applications, because you showed a couple of examples. They're relatively small circuits. It's a presentation, so I know it is not really the core of what you do. But how big can your quantum algorithms be? Yeah, because we will not be able to test it on physical qubits. Yeah, because we have too many errors there. So we have to do it on classical machines. And there we indeed, so I fully join you. It explodes in terms of memory requirements. So you talk about these decision diagrams. is that kind of a computational efficient kind of way of indeed reducing, let's say, a relatively large quantum algorithm into a more compact kind of decision diagram, so that it becomes feasible also to test it on classical computers. That's my main question that I have.
Yeah, thanks, Koen, for the question. And you're absolutely right. And so far, we did all our simulations or evaluations on conventional machines, just because of the reasons you just mentioned. And indeed, of course, we are limited. If we could simulate a very complex quantum algorithm rather efficiently on a conventional machine, then someone would ask the question why we would need quantum computers anymore. So we have our limits. We sort of right now we are evaluating our methods very much on problems like Shor's algorithms, Deutsch algorithm, which is not the most exciting algorithm, but anyway, Grover's algorithm, QFT, and supremacy, quantum advanced benchmarks from Google. So there are a couple of test cases around which the community is using right now. But I completely agree, we are by far not that we have a comprehensive understanding about different classes of quantum algorithms. And frankly spoken, I am the first who would say yes here. So bottom line is basically we really looking forward to get our fingers on real world applications so that we can test and we can evaluate and hopefully improve our method to also other practical relevant quantum algorithms. So far, we're still kind of stuck with Grover, Shor, and these lines of benchmarks, but I completely agree, and we are really looking out for that right now. We have a nice collaboration going on with some colleagues from the medical domain, which want to try out a little bit with quantum algorithms. We need much more of that. We are, as said, we are just at the beginning here, and I hope in the next months and years we're going to be exposed much more to even more practical relevant applications to test our methods and to check how far we get with our methods.
Okay, thank you very much. Thank you.
And this is a very important thing where the community also needs to contribute a little bit, exchanging benchmarks or applications.
Yeah, thank you.
Any further questions from the audience? Okay, if not, then Robert, thanks again for this presentation and participating in this panel. So now I will request Ross and Oliver also to join a common panel, and there might be some questions that all of you can take turns to answer. So again, the floor is open for questions from the audience. So you can put your questions in the chat box, or you can just unmute yourself and ask the question. So let me start with a very general question from the EDA perspective. Again, because the community here is from SIGDA, and the question takes cue from what Robert was presenting at the end, that for some of the problems we are trying to simulate in the classical computer, but we know the classical computer will not be able to do it because it's trying to simulate a quantum computer. So do you see there are upcoming problems where the EDA community has to learn to program in quantum algorithms to solve the EDA problems? Because in the traditional CMOS case, we have seen that the EDA and the complexity of the circuit, it basically had a symbiotic relation. We had more complex computers, and that could run more complex EDA algorithms. So do you see that there is a threshold where we have to program the EDA algorithm itself using quantum computers?
Shall I?
Yeah.
I mean, of course, I don't know for sure what will eventually be done. I think a huge obstacle, and I might be wrong here, so please disagree or I don't know, contradict me. To some extent, this is certainly an issue where we can exploit the power of quantum computers in order to solve corresponding design problems. However, many of the problems have been proven to be NP hard, and to the best of my understanding, right now those problems cannot be efficiently solved with the quantum computer. Might be wrong here, but this is sort of so we might have some problems which even some design problems which even a quantum computer cannot efficiently solve anymore. But please feel free to agree. I'm certainly not a theorist here. I'm just feeling like for some problems it might be a good choice, but probably not for all.
I'm a little bit more theoretical, so I'll just step in and say Robert is right that it's not very plausible that quantum computers will be solving NP-complete problems. At least not the general case, right? So that's always the question. Maybe the case we actually care about, it is quite feasible. I think I also think that a lot of what we would want to do in terms of verification in quantum computers, we don't necessarily need the full power of quantum computers to do that. It's often sufficient to restrict to some more computationally tractable problem, like the nearest Clifford version of the thing you care about, that becomes quite efficient to solve.
Oliver, if you have some perspective on this.
I think the answer so far has been pretty solid, actually. The joke is always maybe you need a quantum computer to build a quantum computer. But MP hard is definitely out of reach. There are lots of examples of places where you can introduce subtle symmetries to quantum circuits that make them efficiently classically computable. A nice example being in the recent Google experiment, for example.
Okay. And also another general question again from the EDA community might be that there are many small sub-problems that you all presented, like in the transpiler or the verification or the routing. So are there some problems where you have open contests going on where the EDA community can start participating and learn step by step? It's, of course, you have the frameworks, but having a contest is a very typical approach in many design automation conferences that we have seen, have been running for past 20, 30 years with much success.
I mean, I'm not sure if I'm supposed to start all the time, but in fact, there are these contests. Oliver, you probably may know that better than me, but the KISK challenge is every year there's a KISK challenge. Actually, the recent one is 3 weeks ago. And this is exactly, you're absolutely right, Anupam, in your assessment. This could get people excited. And we're participating in these challenges for 3 years now. And I think the first challenge, Oliver, you probably know the numbers better. And the first challenge was probably a couple of dozens of people who participate. And in the challenge 2-3 weeks ago, there was 1,000 participants, which actually shows the kind of interest in this thing. And two of my PhD students participated, and we basically blocked the entire week for them, and then they played around, and this kind of community building is taking place. And I think I'm not saying that because Oliver is in the panel, but I think IBM does a great job in powering up the community with events like that. And so it's a great thing. And we
okay. So it was timed with design automation conferences like ICCAD or TEC?
No, it's just online. It's not, maybe Oliver, I'm not sure, you probably know that better. It's just IBM announces that, and then there's 1 week or actually a couple of days where people all over the world sign in and solve the issue.
Yeah. There's also, on the anniversary of the launch of the QX each year, there's a series of kind of more approachable puzzles as opposed to design competition that's designed to bring in people that are maybe not quite, that want to get some exposure to the problems but aren't quite ready to compete at the same sort of level. Those are the ones I do.
Yeah, Ross, maybe you have some inputs here.
I think I was going to say exactly the same thing that Robert said, so I have nothing further to add.
Okay. Any questions from the audience? Okay, maybe what Sungi or Iran, they can continue this activity and try to convert that into something on more regular basis to see the presence of the quantum community in the design automation community, because we have a lot of background knowledge from the conventional EDA systems, and I see that these problems are growing and having a lot of overlap. But there is always a scope to tap into this community by engaging more, and the standard design automation conferences on the architecture conferences, where you can probably come and showcase and give the workshops, tutorials, or organize contests. So this is from my side, this would be a request to the quantum community, I could say. And Robert is actually playing a very nice role to bridge the gap.
Yes, I think Robert already did a lot of efforts in the past. I think he organized several tutorial special sessions in major EDA conferences. I think it's great. And also during this talk, the event today, I think the most audience already learned about the current state of the art of the EDA algorithm, quantum EDA for quantum, and also the recent advance of the quantum architectures. Yeah, because I think most of the audience maybe are not fully familiar with the quantum technology, but I think Oliver did a very good tutorial for today. Yeah, and also the Ross also talk about Ross and also Robert also provide a very good tools or open source tools for people to try it. It's like a very good playground for audience to do the test. That's really good. Yeah.
Maybe one small comment also from my side. A big problem certainly is that the community tackling this problem is rather scattered, or they are organized in different communities. I mean, we have peers who work in, who gather together in companies, in conferences like DATE, IEEE. So our community basically was, I'm pretty sure you're publishing in, I mean, we meet once in a while in some workshops together, but basically our publication venues are different in most of the cases, I guess. I know the computer architecture community has quantum computing sessions and focus, and the software community has that as well. So I always felt a bit hard, and I'm trying to reach out to these other communities, but it's really scattered, and of course it takes a lot of effort because you cannot participate in all the conferences, and the communities, they are thinking differently. So I think that's a huge challenge, because we are working on similar problems, but are scattered around different communities, which makes it sometimes hard.
One good initiative could be from SIGDA or SIGBID, not SIGDA particularly, or SIDA, to organize something in the theme of quantum, because there is a lot of growing problems and there is a lot of people who are able to contribute to research. So it could be SIGDA, special interest group with quantum EDA or something like that, or quantum computing. At IEEE,
yeah. So Robert's quite right that I'm coming from a completely different part of the community. And for example, there is a quantum working group in programming languages in SIGPlan. And that overlaps a lot with the stuff that we've talked about today. I think there's also one in SIGLog as well. So there's a lot of scope for us to get together.
Yeah. Yeah, I think there's a council on superconductivity in IEEE, but it's focused on more on superconductive circuits, I think. But for those on nanowire, ion trap, maybe some different. There's no such a community yet.
It's always good to hear from the people with experimental quantum computing or quantum algorithms background, because then we do actually work on real problems. Otherwise, there is a lot of, say, gap between what we consider as a noise model, what is actually a gate, what is an error correcting code. And this really helps. And I'll thank again for the panelists and the speakers today, and for Shungi and Iran to organize this.
Yeah, thank you. I think all the audience enjoy a lot for the event for today.